Looking out, we are no longer bound to Earth alone. Our planet drifts quietly beneath us, a cradle of life suspended in the vastness. But beyond it, just past that window, the story of space unfolds, not just in moments of triumph, but in whispers of distant worlds and the secrets they hold. There, in the darkness, we can trace the outline of Sputnik, humanity's first tentative step into the cosmic sea. It was more than just a satellite. It was the beginning of an idea. The idea that our future, our destiny, was out there, somewhere in the stars. And while that was the start, it was only the beginning of what would become a deep, endless exploration of the universe. In time, the window opens wider, and we glimpse Yuri Gagarin, the first human to see Earth from space, to feel the pull of the planet fall away as he soared above the curvature of the globe. The stars beyond him were not just points of light, but destinations, uncharted, waiting for discovery. He carried with him not just the weight of history, but the curiosity of every person on Earth who had ever wondered what lay beyond the atmosphere, beyond the pale blue. And then, as the years unfolded, the window revealed new scenes. The grainy footage of Neil Armstrong and Buzz Aldrin stepping onto the moon, their footprints pressed into the dust of another world. It was a single moment of presence on the moon, but it echoed across time, filling us with wonder and possibility. These human journeys into space weren't just missions. They were the first stanzas in a long, unfinished poem about exploration, about seeing what was beyond the next horizon, the next planet, the next star. Through this window, we see not just the destinations we've reached, but the unanswered questions that linger in the night sky. As an astronomer, I often find myself looking beyond the visible stars, past the familiar places like our moon, or Mars, or the icy moons of Jupiter, to the countless exoplanets scattered across the Milky Way. What stories are waiting to be discovered there? In my mind, those distant worlds, planets orbiting stars so far away we can only catch the faintest glimpse of their atmospheres, are somewhere, orbiting a distant star. A planet might hold liquid water, an atmosphere rich with oxygen, or perhaps the faint signature of life. The Kepler Space Telescope. But we are not only looking outward from this window. Space history has also taught us to reflect on our place in the universe. Every satellite, every astronaut, every telescope reminds us that Earth is fragile, that life, this precious, miraculous phenomenon, exists within a delicate balance. Our exploration of space has shown us that we are connected, not just to each other, but to the stars themselves. And from this window, we can also see the future. Missions that will one day take us further, perhaps to Mars or even beyond. The James Webb Space Telescope, poised to peer deeper into the cosmos than ever before, may soon reveal the atmospheres of distant exoplanets, perhaps even signs of life. It will show us new parts of space history, things we cannot yet imagine, questions we have not yet asked. Space history is not a distant memory, but a living, breathing story, one we are writing with each new discovery, with every question we dare to ask. As I look out from this window, I see not just the stars, but the echoes of the past, the whisper of future journeys, and the certainty that we are only at the beginning of our exploration. The universe is vast, its mysteries boundless, and we, like our ancestors who first gazed up at the sky, are only just beginning to understand our place within it. The stars shimmer beyond, vast and endless. Yet within that boundless expanse lies the record of our first humble steps toward the infinite. Each of those steps, Sputnik, Gagarin, Apollo, carries with it the pulse of human curiosity, the relentless drive to understand not just where we are, but where we might one day go. That same drive, pushing us to peer deeper into the cosmos, now brings us to the precipice of new discoveries, as we turn our gaze not just to the stars, but to the worlds orbiting them. Through this window, I think about the worlds we've yet to see with our own eyes, the exoplanets hidden in the light of distant stars, planets we've only begun to detect by watching their stars dim ever so slightly as they pass in front of them. These are the new frontiers of space history, planets that may hold oceans, clouds, and atmospheres filled with the chemical signatures of life. Take the TRAPPIST-1 system, with its 7 rocky planets circling a cool, dim star. From our vantage point, TRAPPIST-1 is just a flicker of light in the constellation Aquarius. But through the lens of our instruments, it becomes a vibrant system full of potential, with planets locked in a delicate gravitational dance. What would it be like to stand on one of those worlds, looking up at the sky and seeing 6 other planets, large as moons, hanging overhead? This is the new space history unfolding. Unlike the Moon or Mars, places we've dreamt of walking on, these exoplanets are so distant that even with our fastest spacecraft, they remain unreachable for now. But through telescopes like Kepler, TESS, and the upcoming James Webb Space Telescope, we are beginning to unravel their mysteries. We can detect their atmospheres, search for water vapor or methane, and speculate whether they are bathed in sunlight or trapped in eternal night. When I look out from this window, I see not just the future, but the delicate balance that connects all of this. How magnetic fields shape stellar winds, how starlight breaks through exoplanetary atmospheres, how the chemistry of a distant world might tell us if life has taken hold there. These aren't just idle thoughts. They're the questions that define the next chapter of space history. And yet, there is always the awareness that we are in the early pages of this history. The space telescopes we've launched are just the beginning. They've shown us the possibility that there are thousands, maybe millions of planets out there like Earth, orbiting their stars at just the right distance for life to flourish. These planets hold the key to answering one of the oldest questions humanity has ever asked. Are we alone? It's incredible to think that the light from those distant worlds, as it passes through their atmospheres, is bringing us answers, slowly, quietly, but surely. That same light, the spectra we observe, carries the fingerprints of life or the lack of it, written in the absorption lines of gases like oxygen, water, and carbon dioxide. But beyond the science, beyond the data, there's something deeply human about this view. We've always looked outward, to the stars, for inspiration and wonder. Now, through the lens of our telescopes and the windows of our spacecraft, we are seeing more than just the faraway stars and planets. We are seeing the seeds of our future. Maybe one day, not too far from now, we'll send missions to some of these exoplanets. Perhaps we'll find one with oceans and breathable air, a place that feels strangely familiar in its distance. Maybe we'll look back on this time, from a future spacecraft window orbiting one of these distant worlds, and think of how far we've come. We'll remember the nights spent gazing up at the stars, wondering if there was life out there, and we'll realize we were already part of something larger, something cosmic. From this window, we are part of space history, and it's still being written. Every discovery, every new exoplanet we identify, brings us closer to the possibility that we're not alone in this universe. The future of space history is unfolding, just beyond our reach, in the atmospheres of distant worlds and the starlight that has traveled millions of years to meet our eyes. Space history is not just about the past or the future. It's about the now, the moment we're in, where our imaginations meet the reality of the cosmos. But more than that, beyond the history that we've written so far, we glimpse the worlds that beckon us forward. Beautiful worlds, strange and wondrous, each with its own story, waiting to be discovered. Through this window, we imagine planets bathed in the light of red suns, skies painted in hues we've never seen on Earth. Worlds like Proxima Centauri b, orbiting the closest star to our own, tantalizingly within reach. Perhaps a place where oceans lap against alien shores under a dim, crimson sky. Proxima Centauri b, our nearest exoplanetary neighbor. Proxima Centauri b, the closest known exoplanet to Earth, orbits the star Proxima Centauri, a red dwarf located just 4.24 light-years away in the Alpha Centauri star system. Discovered in 2016 by the European Southern Observatory (ESO), using the radial velocity method, Proxima Centauri b quickly became one of the most exciting exoplanets ever found. Not only is it close in astronomical terms, practically in our cosmic backyard, but it also lies in the habitable zone of its star, meaning conditions could potentially allow for liquid water on its surface. This discovery makes Proxima Centauri be a prime candidate in the search for habitable worlds beyond Earth. Proxima Centauri b was discovered by measuring these slight wobbles in the movement of its parent star. The planet has a minimum mass of about 1.17 times that of Earth, classifying it as an Earth-like planet or a super-Earth. Its orbital period is about 11.2 days, meaning it completes a full orbit around its star much faster than Earth does around the Sun. Despite this close orbit, Proxima Centauri b lies within the habitable zone, the region around a star where temperatures could allow for liquid water, a key ingredient for life. Because Proxima Centauri is much cooler and dimmer than the Sun, its habitable zone is located closer to the star. Proxima Centauri b orbits at a distance of about 5 cents, astronomical units, only 5% of the distance between Earth and the Sun. While this might sound perilously close, the reduced luminosity of Proxima Centauri means that the planet receives roughly the same amount of starlight as Earth does from the Sun. A tidally locked world? One of the most intriguing, yet potentially challenging, aspects of Proxima Centauri b is the likelihood that it is tidally locked. This means that one side of the planet constantly faces its star, while the other side remains in perpetual darkness, much like the Moon's relationship with Earth. If Proxima Centauri b is indeed tidally locked, it would have extreme temperature variations between its day side and night side, with one hemisphere receiving continuous sunlight and the other shrouded in eternal darkness. The day side could be blisteringly hot, with direct exposure to Proxima Centauri's radiation, while the night side might be freezing cold. However, in the Terminator Zone, the region between the day and night sides, temperatures might be more moderate, potentially creating habitable conditions. In this twilight region, liquid water might exist, and life, if present, could potentially thrive in this narrow band where conditions are more stable. If Proxima Centauri b has a thick atmosphere, it could help redistribute heat from the day side to the night side, reducing the temperature extremes. In this scenario, atmospheric circulation would play a crucial role in shaping the planet's climate, allowing for more uniform temperatures across the surface. Oceans, if they exist, could also help moderate the climate by transporting heat, making the planet more hospitable for life. The possibility of an atmosphere, whether or not Proxima Centauri b has an atmosphere, is one of the central questions regarding its potential habitability. A thick atmosphere would not only help moderate the planet's climate, but it could also protect the surface from harmful stellar radiation. However, the stellar flares from Proxima Centauri could have significant consequences for the planet's atmosphere, potentially stripping it away over time. Stellar flares emit high-energy particles and radiation that could erode a planet's atmosphere, particularly on planets orbiting close to their star, like Proxima Centauri b. Without a strong magnetic field or a protective atmosphere, Proxima Centauri b could be exposed to harmful radiation, making it difficult for life to survive on the surface. Despite these challenges, some models suggest that Proxima Centauri b might have retained its atmosphere, possibly due to a strong magnetic field or other protective factors. If the planet does have an atmosphere, it would be key to understanding its potential for habitability. Future missions and telescopes, such as the James Webb Space Telescope, may be able to study the atmospheric composition of Proxima Centauri b, providing critical data about its environment. Proxima Centauri's flares and their impact. One of the major hurdles to life on Proxima Centauri b is the intense stellar activity of its parent star. Proxima Centauri, like many red dwarfs, regularly emits stellar flares, bursts of radiation that can dramatically increase the amount of ultraviolet and X-ray radiation hitting the planet. These flares can strip away the atmosphere and damage any potential biosphere. A 2017 observation captured one of the largest flares ever seen from Proxima Centauri, which temporarily increased the star's brightness by a factor of 1,000. Such flares, if frequent, could be devastating for a planet like Proxima Centauri b. However, some scientists believe that if the planet has a sufficiently thick atmosphere or a strong magnetic field, it could still retain habitability in certain regions. One possibility is that life on Proxima Centauri b, if it exists, could have adapted to these flares. Life forms might evolve to thrive underground or beneath oceans, where they would be shielded from the most harmful radiation. Alternatively, life could exist in the shadowed side of the planet, protected from the intense radiation of its flaring star. Potential habitability and the search for life. Despite the challenges posed by its proximity to a flare star and potential tidal locking, Proxima Centauri b remains one of the most promising candidates for habitability outside of our solar system. If liquid water exists on the surface and the planet has retained its atmosphere, Proxima Centauri b could harbor life, possibly in environments similar to the deep ocean ecosystems on Earth. The potential for life in the twilight zone, where temperatures are more stable, is one of the most exciting aspects of the planet's discovery. In such a scenario, the interplay between light and dark could create complex ecosystems that are shaped by the unique environment of a tidally locked world. Even if life does not exist on the surface, it is possible that microbial life could survive in subsurface environments, protected from the harsh conditions above. In the coming years, astronomers hope to study Proxima Centauri b in greater detail. Instruments like the James Webb Space Telescope and ground-based observatories will allow scientists to analyze the light from Proxima Centauri b as it passes through the planet's atmosphere, searching for signs of water vapor, oxygen, and other gases that could indicate habitability. Breakthrough Starshot, an ambitious project backed by physicist Stephen Hawking and billionaire Yuri Milner, aims to send small, light-powered spacecraft to the Alpha Centauri system within the next few decades. These probes, if successful, could provide direct imaging and data on Proxima Centauri b, offering an unprecedented glimpse into this nearby world. A vision of Proxima Centauri b. What might Proxima Centauri b look like? Imagine standing in the twilight zone, with one side of the sky glowing with the faint light of a red dwarf star, while the other side fades into deep, endless night. The atmosphere, if present, might be thick with clouds, and strong winds could sweep across the surface as heat from the day side is carried to the night side. In the distance, towering storms could form on the day side, where the constant heat drives powerful weather patterns. Oceans, if they exist, might be churning under the pull of the planet's tidal forces, with waves crashing onto dark, rocky shores in the twilight. On the night side, the temperature could drop dramatically, freezing the oceans and creating vast expanses of ice. Beneath the surface, in the depths of the ocean or within the planet's crust, life could thrive, adapted to survive in extreme conditions, shielded from the radiation above. Microbial life, similar to the extremophiles that survive in Earth's harshest environments, could be the dominant form of life here, clinging to the narrow regions where conditions are just right for survival. The future of exploration. Proxima Centauri b is not just a curiosity, it's a target. Its proximity to Earth means that it's one of the few exoplanets we may be able to study in detail within our lifetimes. Future missions to the Alpha Centauri system, combined with next-generation telescopes, may allow us to determine once and for all whether this planet is habitable or even inhabited. Could we one day walk there, feel the faint warmth of a different star on our skin, and look up to see unfamiliar constellations? Then there is Kepler 452b, a world that has been called Earth's cousin. Orbiting in the habitable zone of a star much like our Sun, Kepler 452b might be covered in green, its landscape lush and fertile, with thick clouds drifting lazily above a landscape of towering mountains and deep valleys. There perhaps rain falls just as it does here, nourishing life that grows and evolves, untouched by human hands but connected to us by the same cosmic forces that shaped our own Earth. And what of the worlds that circle distant stars like LHS 1140b, a rocky planet just 40 light-years away? Its gravity might be stronger, the air heavier, but with an atmosphere rich in possibilities. Perhaps dense clouds swirling across a cobalt-blue horizon, with winds carrying the scent of alien oceans. Thick with life we have yet to imagine. The light there might be faint, a soft glow from its red dwarf star, casting the landscape in perpetual twilight, a world forever on the cusp of dawn or dusk. In the TRAPPIST-1 system, 7 rocky worlds orbit a cool, dim star, each unique and beautiful in its own right. Imagine standing on one of those planets, with the other 6 hanging low in the sky, like moons. The sunsets there might be like nothing we've ever seen. Deep purple skies fading into amber, with bands of starlight filtering through the thin atmosphere. What life could thrive in such a place, under the gentle glow of an ultra-cool star, where days stretch long and the warmth is ever so faint? Beyond the stars we know, there are surely worlds that defy all expectations. Planets where seas of methane glisten under emerald skies, or where clouds of ammonia rise high above mountains of ice. There could be gas giants with moons as beautiful and varied as the planets themselves, some covered in tropical storms that rage for centuries, others with crystal-clear oceans that reflect the stars as though they were mirrors. And there might be water worlds, entire planets covered in oceans, with endless waves stretching from horizon to horizon, warmed by a distant sun and teeming with life in its depths. One can only dream of the beauty of a world like Gliese 581g, an exoplanet that orbits its star in the habitable zone, where the temperature is just right for liquid water. Perhaps this world is cloaked in mists, its surface obscured from our distant gaze, a place where life flourishes under the watchful eye of a red sun. Trees with leaves dark as night might stretch toward the sky, gathering every last photon of light, while rivers of crystal-clear water carve paths through fertile plains, home to creatures as varied and wondrous as the ecosystems of Earth. Gliese 581g, a potentially habitable exoplanet. Gliese 581g is one of the most intriguing exoplanets ever discovered, orbiting a star just 20 light-years away from Earth. Found in 2010 by astronomers using the Keck Observatory in Hawaii, Gliese 581g quickly captured the imagination of scientists and space enthusiasts alike because it lies in what's known as the habitable zone, the region around a star where conditions may be just right for liquid water to exist. This discovery led to speculation about whether Gliese 581g could support life, making it a focal point in the search for Earth-like exoplanets. The star, Gliese 581. Gliese 581g orbits a star called Gliese 581, a red dwarf located in the constellation Libra. Red dwarfs are smaller, cooler, and much dimmer than our Sun, but they're the most common type of star in the universe. Despite being much less luminous, red dwarfs often have long, stable lifespans, meaning planets orbiting them could enjoy relatively stable conditions for billions of years, an important factor in the potential for life to develop. Gliese 581, like many red dwarfs, is a star that exhibits stellar flares, sudden bursts of energy that can release powerful radiation. This type of activity could be a challenge for habitability, particularly for planets close to the star. However, because Gliese 581g lies right in the middle of the habitable zone, there is hope that its atmosphere, if it exists, could protect the planet from such radiation, creating a stable environment on the surface. The discovery of Gliese 581g. The discovery of Gliese 581g was made by analyzing the radial velocity of the star, essentially how the star wobbles due to the gravitational pull of orbiting planets. This technique allowed astronomers to detect multiple planets in the Gliese 581 system, including Gliese 581g, which was found to orbit in the star's habitable zone. The planet itself is estimated to be a super-Earth, meaning it is larger than Earth, but smaller than gas giants like Neptune. Gliese 581g was initially thought to be about 3 to 4 times the mass of Earth, with a radius about 1.5 times larger than our planet. Its year, one complete orbit around its star, takes just 37 days, meaning it is much closer to Gliese 581 than Earth is to the Sun. However, because Gliese 581 is a dim red dwarf, this proximity places Gliese 581g right in the sweet spot of the habitable zone, where temperatures could allow for liquid water to exist on its surface. Could Gliese 581g support life? One of the most exciting aspects of Gliese 581g is its potential to harbor liquid water, which is considered essential for life as we know it. If Gliese 581g has an atmosphere, it could act as an insulating layer, helping to regulate the planet's temperature and possibly allowing for oceans or lakes of liquid water. However, there's an important caveat: tidal locking. Like many planets orbiting red dwarfs, Gliese 581g is likely tidally locked, meaning one side of the planet is always facing the star, while the other side is in perpetual darkness. This could result in extreme temperature differences between the day side and the night side. The side facing the star might be extremely hot, while the dark side could be freezing cold. But between these two extremes, there could be a twilight zone, a region where temperatures are moderate enough to allow for liquid water and potentially life. In this twilight zone, temperatures could be mild, and if there is water, it might flow in the form of rivers or pool into lakes or seas along the boundary between light and dark. The presence of an atmosphere would be key here. A thick enough atmosphere could help distribute heat around the planet, creating a more temperate climate across larger regions, rather than just at the boundary. The possibility of an atmosphere. To date, we don't know whether Gliese 581g has an atmosphere, and that remains one of the planet's greatest mysteries. If it has a substantial atmosphere, it could protect the surface from the stellar flares emitted by Gliese 581 and help regulate the planet's temperature. The atmosphere could also provide clues to the possibility of life. If we were able to observe the planet's atmosphere in detail, we would look for specific markers such as water vapor, oxygen, methane, and carbon dioxide. These gases are associated with the processes of life on Earth, and their presence on Gliese 581g could be a promising sign of biological activity. However, even without these specific markers, an atmosphere that provides the right conditions for liquid water would be an exciting discovery. In the absence of an atmosphere, Gliese 581g would likely be a barren, inhospitable world. Without atmospheric pressure to keep water in liquid form, any surface water would either freeze solid on the dark side or evaporate into space on the day side, making the planet unlikely to support life as we know it. The controversy. Despite the initial excitement, the existence of Gliese 581g was later called into question by some astronomers. In 2014, new data suggested that what appeared to be a signal for Gliese 581g might actually be caused by stellar activity, specifically magnetic activity on the surface of the star. This stirred debate within the scientific community, with some researchers arguing that Gliese 581g's discovery could have been a false positive. However, the controversy did not fully close the case on Gliese 581g. Some astronomers still believe that the planet exists, but that more detailed observations are needed to confirm its presence. The Gliese 581 system remains a prime target for further study, as other planets in the system, including Gliese 581d, also lie near the habitable zone, making it one of the most promising nearby star systems in the search for habitable worlds. The future of Gliese 581g exploration. While Gliese 581g's status remains uncertain, It highlights the challenges and excitement of discovering potentially habitable exoplanets. Future telescopes, such as the James Webb Space Telescope, are expected to bring us much closer to understanding distant worlds like Gliese 581G. These instruments will be able to analyze the light passing through exoplanet atmospheres, providing detailed information about their composition and structure. In the case of Gliese 581G, one of the most important steps would be to confirm its existence and then focus on determining whether it has an atmosphere. If we find that it does, the next step would be to search for signs of habitability, such as the presence of water vapor or other biosignatures. Even if Gliese 581G proves not to exist, the search for Earth-like exoplanets in the habitable zones of nearby stars will continue. Red dwarfs like Gliese 581 are prime targets because their small size and cooler temperatures make it easier to detect planets orbiting close by. The discovery of Gliese 581G has already shifted the focus of exoplanet research toward these small, dim stars, where the potential for habitable worlds might be greater than we ever imagined. A vision of Gliese 581G. If Gliese 581G does exist, what might it look like? Imagine standing on the surface of a tidally locked planet, with one side forever bathed in light and the other shrouded in eternal darkness. In the twilight zone, the sky could glow with a pale orange or red hue, reflecting the soft, dim light of its red dwarf star. The landscape might be rocky and barren in places, but along the edge of the light, liquid water could flow in rivers and collect in seas. The air could be dense with moisture, swirling in patterns that balance the extreme temperatures between the two sides of the planet. As you look toward the bright horizon, you might see storm clouds gathering, where heat from the star drives intense weather systems. Behind you, the sky fades into deep darkness, where the stars glimmer coldly over a frozen landscape. Life, if it exists, might cling to the borderlands, where the balance of light, water, and temperature creates just the right conditions for survival. In the search for life beyond Earth, Gliese 581G remains one of the most fascinating and enigmatic possibilities. Whether it proves to be a real planet or just a false signal, its discovery has opened our eyes to the potential of the universe, showing us that the ingredients for life could be scattered across the cosmos, waiting for us to find them. And what about the mysterious water-rich planets that might exist in abundance? Imagine a planet where entire continents float on vast, deep oceans, their surfaces dotted with archipelagos of glowing bioluminescent life. Beneath the waves, ancient creatures swim through the depths, their movements slow and graceful, as if the oceans themselves breathe in time with the tides of their distant star. The skies above these water worlds might shimmer with auroras, caused by magnetic fields far more powerful than anything we know on Earth, creating dazzling displays of light as particles from their parent stars interact with the planet's atmospheres. Perhaps the most beautiful worlds are those that challenge our understanding of what life can be. Planets that orbit binary stars, where two suns cast overlapping shadows, creating twilight zones where life might flourish in the delicate balance of light and dark. The landscapes of these worlds could be otherworldly, sand dunes stretching out under two suns, with deep canyons carved by the winds that howl through them. Or perhaps the surface is dotted with glassy lakes that reflect both stars, their surfaces rippling in the wind like pools of liquid light. As we look out from this window, we are filled with a sense of awe and possibility. The universe is not a cold, empty place, but a canvas filled with vibrant worlds, each one with its own unique beauty and its own story to tell. The light from these distant planets has traveled for thousands, millions, even billions of years to reach us. And as we study that light, we begin to understand that the beauty of the universe is far more complex and diverse than we ever imagined. Each of these worlds, seen or unseen, represents a new chapter in the story of space exploration, a chapter that humanity has only just begun to write. We have sent our robotic explorers to the edges of our own solar system, but the real journey is just beginning. With each new telescope, each new mission, we are opening windows into new worlds, revealing the wonders of the universe one planet at a time. These beautiful worlds, with their alien skies, unfamiliar landscapes, and untold secrets, are waiting for us. They are out there, just beyond our reach, but closer than ever before. Through the light we capture, through the missions we send, and through the dreams we pursue, we are getting closer to understanding not just the universe, but our place within it. And one day, perhaps, we will stand on one of those beautiful worlds, looking up at a new sky, knowing that from a window long ago, we first caught a glimpse of the vastness and beauty that awaited us. In the tapestry of the cosmos, there are few phenomena as captivating and mysterious as binary stars, pairs of stars bound together by gravity, orbiting a common center of mass. These celestial duos are not rare. In fact, nearly half of all stars in the universe are part of binary or multiple star systems. But it is their dynamic, complex relationships that make them so fascinating. As we peer through the window of space exploration, we catch glimpses of these systems and the planets that might orbit within them, revealing a universe far more intricate than we once imagined. A cosmic dance of light and gravity. At first glance, binary stars may appear similar to the solitary stars we're familiar with, like our own Sunday. But these pairs of stars are locked in a delicate dance, their gravitational pulls keeping them in constant motion around one another. This movement creates a cosmic ballet, where the stars orbit a common center of mass, sometimes so close they nearly touch, and at other times separated by vast distances. Some binary star systems are composed of stars of similar size and brightness, while others are more extreme, with one star much larger or more massive than its partner. These contrasting pairs, like the supergiant and dwarf binaries, create extraordinary contrasts in their interactions. Massive, radiant stars pulling on their smaller companions with such force that their outer layers are sometimes stripped away, feeding the larger stars insatiable energy. Binary stars can vary in their proximity and relationship to each other. Closed binaries orbit in such tight proximity that they can exchange material, often resulting in dramatic stellar phenomena like novae, or even the eventual merger of the two stars into a single, more massive one. In contrast, wide binaries may orbit at distances so great that they take thousands of years to complete a single revolution, appearing more like two independent stars from an observer's perspective. These wide systems can have planets orbiting one or both stars in intricate orbital resonances, creating a complex and dynamic environment for any planetary system. Two suns in the sky, the worlds of binary stars. One of the most mesmerizing ideas about binary stars is imagining what it would be like to live on a planet orbiting such a system. Picture a sky with two suns, each casting its own unique light across the landscape. In some binary systems, one sun may be larger and brighter, dominating the day, while the other is smaller, offering a softer, secondary light that waxes and wanes as the stars move through their orbital paths. The skies of such a world would shift dramatically, with the dance of the suns creating days and nights that vary in brightness and length. Some planets orbit both stars in what is called a circumbinary orbit, where the planet circles around the entire binary pair, much like the fictional planet Tatooine from Star Wars, which famously had two suns in its sky. These circumbinary planets must navigate the gravitational tug-of-war between the two stars, creating highly stable orbits in some cases and chaotic, unpredictable paths in others. For a planet in such a system, the rhythm of the star's motion could cause dramatic shifts in temperature and light, leading to seasons more extreme than anything we experience on Earth. In other binary systems, planets orbit just one of the stars while the second star orbits at a greater distance. These planets experience regular changes in their sky as the second star comes into view and then fades away, potentially leading to periods of double sunrises or sunsets. Imagine standing on a planet like this, watching one sun set in the west, while the other hovers low on the horizon, its light casting a soft glow long into the evening. Kepler 16b, a circumlunar planet discovered by the Kepler Space Telescope, is a real-world example of this. It orbits a pair of stars in the constellation Cygnus, and its skies would be a stunning display of celestial choreography, with two suns rising and setting in sync with the planet's orbit. The discovery of Kepler 16b was a watershed moment, proving that planets can indeed exist in stable orbits around binary star systems, and opening up new possibilities for where we might find habitable worlds. The science behind binary stars, interactions, and evolution. The relationship between two stars in a binary system can be as peaceful as it is violent. In close binary systems, where the stars are near enough to influence each other's evolution, a process known as mass transfer can occur. When one of the stars in a close binary begins to swell into a red giant at the end of its life, its outer layers can spill over onto its companion. This can result in one star growing significantly in mass, while the other shrinks or even loses its outer layers entirely, becoming a white dwarf or another compact stellar remnant. The most extreme version of this process occurs in contact binaries, where the two stars are so close that they share a common outer envelope of gas. These systems are often unstable and can eventually merge into a single star, or they can result in dramatic stellar explosions such as a nova, when material from one star falls onto a white dwarf, leading to a thermonuclear explosion that briefly outshines an entire galaxy. In some cases, binary stars can end their lives in spectacular fashion. If both stars in the system are massive enough, they may both go supernova, leaving behind two neutron stars or black holes orbiting one another. These stellar remnants can continue their dance, spiraling closer and closer together as they lose energy in the form of gravitational waves. Ripples in space-time predicted by Einstein's theory of general relativity and detected for the first time by the LIGO Observatory in 2015. When two neutron stars, or black holes, finally collide, they release a burst of energy so powerful that it can be detected across the universe. Habitability around binary stars. Life in a dynamic sky. One of the most exciting questions surrounding binary stars is whether life could arise on planets orbiting these systems. The complex gravitational interactions between two stars create unique environments, but they do not necessarily exclude the possibility of life. In fact, binary systems may offer some advantages. For planets in circumlunar orbits, the combined gravitational pull of the two stars can create highly stable orbital regions, known as habitable zones, where conditions might allow liquid water to exist on the surface. In such systems, the changing light from two suns could lead to fascinating variations in climate and weather, potentially giving rise to life forms adapted to fluctuating conditions. Planets orbiting just one of the stars in a binary system might also experience periods of enhanced energy as the second star approaches, potentially boosting photosynthesis and other biological processes. Life on such worlds could evolve to take advantage of these cycles, thriving during the times when both stars' light reaches the planet's surface and entering periods of dormancy or reduced activity when one star recedes. However, binary star systems also present challenges. The complex gravitational dynamics can make planetary orbits less stable, and the intense radiation from certain types of stars, such as red giants or massive blue stars, could pose significant hurdles for life. But the discovery of planets like Kepler 47c, a gas giant orbiting a binary star, suggests that planet formation is possible in these systems, and where there are planets, the potential for life remains. The next frontier, exploring binary systems. As we peer deeper into the universe, the study of binary stars will continue to play a crucial role in our understanding of stellar evolution and the search for habitable worlds. With the advent of advanced telescopes like the James Webb Space Telescope, we are poised to explore these systems in even greater detail. JWST will allow us to observe the atmospheres of exoplanets orbiting binary stars, helping us determine whether these distant worlds could support life. Future missions could also send probes to the Alpha Centauri system, the closest binary star system to Earth, located just over 4 light-years away. Alpha Centauri consists of 2 stars, Alpha Centauri A and Alpha Centauri B, with the possibility of a third star, Proxima Centauri, which has its own planet, Proxima b. These stars offer a tantalizing opportunity to study a binary system up close and to explore the potential for habitable planets in our cosmic backyard. As we gaze through the window into the night sky, we realize that binary stars are not just astronomical curiosities. They are dynamic systems filled with potential for discovery. Whether through the drama of stellar collisions, the gentle dance of 2 suns, or the prospect of life under a dual star system, binary stars remind us that the universe is far more diverse and intricate than we ever imagined. They are a testament to the beauty and complexity of the cosmos, a cosmic dance of light, gravity, and time that continues to unfold before our eyes. 2 suns in the sky, the worlds of binary stars. Imagine standing on the surface of a distant planet, and instead of one familiar sun hanging in the sky, there are 2, each casting its own light, each pulling on the planet in its own way. In binary star systems, this isn't just science fiction, it's reality. For any planet that orbits 2 stars, the rhythm of day and night, the changing seasons, and even the color of the sky could be profoundly different from what we experience here on Earth. The worlds of binary stars offer a fascinating glimpse into the incredible diversity of planetary environments across the cosmos, where dual suns create landscapes, climates, and atmospheres unlike anything we've ever seen. The beauty of a binary sky. On a planet orbiting a pair of stars in a circumbinary orbit, the sky would be in constant flux, influenced by the shifting positions of its 2 suns. Depending on the distance between the stars and the planet, the 2 suns might rise and set together, or at different times, creating a spectacular dance of light. Imagine watching one sun dip below the horizon, casting long shadows across the landscape, while the other remains high in the sky, bathing everything in a warm, second light. The interplay between the 2 stars could paint the sky with colors unseen on Earth. Brilliant oranges, deep purples, and even hues of green or red, depending on the spectral types of the stars involved. In some cases, the stars might be very different from one another. One could be a hot, bright blue star, radiating intense ultraviolet light, while the other is a cooler, dimmer red dwarf. This stark contrast would create fascinating effects on the planet's surface. The cooler star might create a softer, more diffuse light, while the hotter star shines with piercing brilliance. The dual light sources could cast overlapping shadows, creating a surreal landscape of shifting brightness and color. The changing positions of the suns could also create unique weather patterns. In some parts of the planet's orbit, both suns might shine equally bright, raising the temperature significantly, while in other parts, the stars could be farther apart in the sky, casting the planet into periods of cooler light. These fluctuations could lead to extreme seasons or even regions where one side of the planet is locked in perpetual twilight, while the other basks in daylight from both stars. The physics of circumbinary orbits. For a planet to exist around a binary star system, it must follow a delicate path. Circumbinary planets, those that orbit both stars, must balance the gravitational pull of 2 stellar bodies while maintaining a stable orbit. The region in which a planet can safely orbit is called the circumbinary habitable zone, and it is shaped not only by the heat and light of the stars, but also by the gravitational interactions between them. In close binary systems, where the stars orbit each other tightly, the habitable zone for a circumbinary planet is typically farther out, where the planet can experience a more stable gravitational environment. In wider binary systems, the habitable zone can be closer to the stars, allowing for the possibility of planets that can sustain liquid water and, potentially, life. Planets that orbit both stars at a safe distance experience a unique but stable gravitational balance. The gravitational pull from each star creates a wobble in the planet's orbit, but this wobble can settle into a rhythm that keeps the planet in a stable path around the binary pair. This means that while the gravitational forces are more complex than those of a planet orbiting a single star, it's entirely possible for planets to exist in these systems for billions of years, long enough for life to evolve. Kepler 16b, as mentioned earlier, is a prime example of a circumbinary planet. It orbits two stars, a K-type and an M-type dwarf, both cooler and smaller than the Sun. While Kepler 16b is a gas giant and not likely to harbor life, its discovery was a major breakthrough, proving that stable planetary orbits can exist around binary stars. It was also a confirmation that planets in such systems might be more common than we once thought. Seasons and climate on a circumbinary planet. On a planet orbiting two suns, the concept of seasons would be far more complex than on Earth. Seasons on our planet are caused by the tilt of the Earth's axis as it orbits the Sun, leading to variations in sunlight across the year. But on a circumbinary planet, the positions of the stars relative to one another could create dual seasonal cycles, one influenced by the planet's orbit around both stars, and another caused by the changing positions of the stars in relation to each other. During certain parts of the year, the two suns might align, bathing the planet in double the amount of light and heat. This could create super summers, periods of intense warmth and bright light. Conversely, when the stars are on opposite sides of their orbit, their combined light might be weaker, plunging the planet into cooler, dimmer seasons, what we might call superwinters. The ebb and flow of these dual solar influences would create complex climate patterns, perhaps even leading to exotic weather phenomena such as extreme wind patterns, fluctuating ocean currents, or rapidly changing cloud formations. Some circumbinary planets might experience binary eclipses, where one star passes in front of the other. This could lead to brief periods where the planet is shaded from the light of one of its suns, creating a temporary cooling effect similar to an eclipse on Earth, but potentially lasting longer or affecting the entire planet. Such events could have dramatic effects on the planet's ecosystem and climate, causing rapid shifts in temperature and light levels. The habitability of planets with two suns. One of the most exciting prospects in the study of binary star systems is the potential for habitable planets, worlds with the right conditions for liquid water and life. While binary star systems were once thought to be unlikely hosts for life, the discovery of circumbinary planets like Kepler 16b and others has shown that these systems can indeed support stable planetary orbits. The question now is whether any of these planets could be located in the habitable zone, the region where temperatures are just right for liquid water to exist. In binary systems where both stars are relatively small and cool, such as two M dwarfs or a combination of an M dwarf and a K dwarf, the habitable zone could be closer to the stars. In these systems, a planet in the habitable zone might experience milder temperatures, with the combined light from the two stars providing enough warmth for liquid water without overwhelming the planet with radiation. Conversely, in systems where one or both stars are much hotter and more massive than the Sun, the habitable zone would be farther out, where the combined heat and radiation of the two stars would be more balanced. These planets might orbit farther away, but could still receive enough energy to support life. The presence of two suns could also offer certain advantages, such as a more stable climate over long periods of time, as the stars' gravitational interactions could help keep the planet's orbit in a stable, predictable path. The atmosphere of a planet in a binary star system would play a crucial role in determining its habitability. With two stars emitting varying levels of radiation, the planet's atmosphere would need to be thick enough to shield the surface from harmful ultraviolet and X-rays, particularly if one or both stars are more active than our Sun. At the same time, The atmosphere would need to allow enough light and warmth to reach the surface to support life. On a binary planet, the interaction of two stars could create stunning atmospheric effects. Perhaps vibrant auroras caused by the magnetic fields of the two stars, or clouds that glow in the light of both suns. The mysteries yet to unfold. As we continue to discover more about binary star systems and their planets, the potential for life in these worlds remains one of the most tantalizing questions in astronomy. With missions like the James Webb Space Telescope and upcoming observatories designed to study exoplanets in detail, we are on the cusp of a new era of exploration. These powerful instruments will allow us to probe the atmospheres of circumlunar planets, searching for signs of water vapor, oxygen, and other biosignatures that could hint at the presence of life. Binary star systems, with their dual suns and complex gravitational dynamics, are just one of the many types of planetary systems that challenge our understanding of the universe. They remind us that the cosmos is far more diverse and surprising than we ever imagined, with environments that push the boundaries of what we think is possible. And as we gaze through our telescopes, looking for new worlds, it's entirely possible that the next great discovery in the search for life beyond Earth could come from a planet orbiting two suns, a world where two stars light the sky, and where the story of life is being written in the glow of their combined brilliance. Water-rich planets, oceans beyond Earth. Water, the foundation of life as we know it, is not unique to Earth. In the vastness of the cosmos, scientists believe there are entire planets where water is not just present, but abundant. These water-rich planets, sometimes referred to as ocean worlds, represent some of the most intriguing destinations in the search for life beyond our solar system. Imagine worlds where oceans stretch unbroken from horizon to horizon, where the land, if it exists at all, is submerged beneath kilometers of liquid water. These alien oceans, while familiar in substance, could hold secrets and surprises far beyond our understanding. The science of water worlds. Water-rich planets are believed to have formed in the colder, outer regions of their planetary systems, where water ice was plentiful during the formation of the planet. These worlds may have migrated closer to their stars over time, bringing their vast reservoirs of water with them. Unlike Earth, where water covers roughly 70% of the surface but remains relatively shallow in comparison to the planet's overall size, water-rich planets may be dominated entirely by deep oceans. Oceans that could be hundreds, even thousands, of kilometers deep. In these worlds, water would likely be a fundamental part of the planet's structure, creating unique layers of ice and liquid depending on the temperature and pressure. Beneath the vast surface oceans, immense pressures at deeper levels would force water into different forms, such as high-pressure ice, which is not the frozen water we know, but a denser, more solid form of ice that can exist even at high temperatures. This layering effect could create entirely alien ocean ecosystems, where life might thrive in environments more extreme than anything found on Earth. Some water-rich planets may even contain an ice mantle, a layer of ice beneath the liquid water, formed by the immense pressure of the overlying ocean. Such a planet could still have active geological processes below this ice mantle, similar to Earth's mantle and core. In these cases, hydrothermal activity could occur where the planet's internal heat causes cracks in the ice, releasing heat and chemicals into the deep oceans above. Such environments would be similar to Earth's deep-sea hydrothermal vents, where life thrives despite the absence of sunlight. Oceans that cover the world. Imagine standing on the surface of one of these planets, if you could. The view would be unlike anything you've ever seen. An endless expanse of water stretching out in every direction, with no land in sight. The atmosphere might be thick with moisture, constantly feeding the ocean below with rains or creating immense clouds that hover above, reflecting the light of a distant star. The color of the water could vary depending on the planet's chemistry and the light of its sun, from deep blues to greens or even darker hues. colored by unknown elements or biological life lurking beneath. These water worlds could have unique weather systems, driven by the interaction between the ocean and atmosphere. Without land to break up weather patterns, massive storms could form, with winds and waves far more intense than anything we've seen on Earth. On some water-rich planets, superstorms could last for centuries, driven by constant heat exchange between the ocean and atmosphere, creating monstrous waves and towering clouds that spiral across the surface. The deeper oceans would likely be completely alien environments. On Earth, our deepest oceanic trenches extend about 11 kilometers below the surface. But on water-rich planets, these depths could be multiplied many times over. At such depths, life from the surface would be entirely absent, creating a dark, pressurized world where exotic forms of life could evolve. Chemosynthesis, a process where life forms derive energy from chemicals rather than sunlight, could be widespread, just as it is at Earth's deep-sea vents. The creatures on these planets, if they exist, might be adapted to live in complete darkness and under incredible pressure. They could be unlike anything we've ever encountered. Large, slow-moving organisms that glide through the deep waters, or entire ecosystems based on floating mats of microbial life drifting just below the surface. The possibilities for life on such planets are vast and, as yet, unexplored. The atmospheres of water-rich planets. The atmosphere of a water-rich planet would be an essential factor in determining its habitability. In many cases, water worlds may have dense, thick atmospheres rich in water vapor, creating a greenhouse effect that keeps the surface warm and stable, even if the planet is far from its star. The James Webb Space Telescope and other future missions will allow us to study these atmospheres in detail, searching for signatures of water vapor, clouds, and other gases that could indicate the presence of oceans and potentially life. On some water-rich planets, the atmosphere could be in constant flux. The vast surface oceans could contribute to rapid evaporation, creating an atmosphere heavy with moisture. This moisture could condense into massive cloud systems that circle the planet, creating endless rainstorms and contributing to the planet's dynamic weather. In some cases, these atmospheres could be so thick with water vapor that they create a steam world, where the surface is a boiling ocean of water vapor and liquid, surrounded by towering clouds. In more temperate water-rich planets, the atmosphere might resemble Earth's, with a balance of nitrogen, oxygen, and water vapor, possibly giving rise to clouds, rain, and even snow. However, the lack of land to anchor weather systems could mean that the entire planet is subject to frequent and powerful storms, with winds and waves far stronger than anything seen on Earth. In terms of habitability, the presence of liquid water is a key factor, but the atmosphere also needs to protect the surface from harmful radiation and provide a stable environment for life to thrive. Water-rich planets orbiting M-dwarf stars, which are known for their intense flares and radiation, would need a thick, protective atmosphere to shield the oceans from these bursts of energy. In some cases, the thick atmosphere of a water world could help regulate temperatures and protect against such radiation, allowing life to evolve in the oceans below. Europa, Enceladus, and the ice moons, clues from our own solar system. While exoplanets with vast oceans are a tantalizing prospect, we don't have to look far from home to find examples of potential water-rich worlds. Some of the most intriguing candidates for oceans beyond Earth lie within our own solar system, on moons like Europa and Enceladus. Europa, one of Jupiter's largest moons, is covered in a thick shell of ice. Beneath that icy crust, scientists believe there is a global ocean of liquid water, kept warm by tidal forces from Jupiter's gravity. The Europa Clipper mission, set to launch later this decade, aims to investigate Europa's subsurface ocean, searching for clues about its composition and whether it might harbor life. If Europa's oceans contain hydrothermal vents or other sources of chemical energy, it could be a prime location for extraterrestrial life, living in the dark, cold waters beneath the ice. Similarly, Enceladus, a small moon of Saturn, has captivated scientists since the discovery of water ice plumes shooting from its south pole. These plumes, which contain organic compounds, are thought to originate from a subsurface ocean beneath the moon's icy crust. The heat required to keep this ocean from freezing likely comes from geological activity, similar to what we see in Earth's oceans near hydrothermal vents. These plumes have been sampled by the Cassini spacecraft, and the findings suggest that Enceladus could be another potential home for life. While these moons are much smaller than the exoplanets we imagine, they offer critical clues about how water-rich worlds might form and behave. Studying Europa, Enceladus, and other ocean moons gives us a blueprint for understanding how deep oceans can exist in environments far from the warmth of the sun and how life might thrive in such extreme conditions. Super-Earths and sub-Neptunes, likely water-rich planets. Many of the exoplanets discovered by the Kepler Space Telescope and other missions fall into a category known as super-Earths or sub-Neptunes, planets larger than Earth but smaller than Neptune. These planets are thought to be some of the most likely candidates for water-rich worlds. Their size and density suggest that they may have large amounts of water, potentially covering their surfaces or existing as thick layers beneath the atmosphere. For example, the exoplanet Kepler-22b, located in the habitable zone of its star, is believed to be a super-Earth with a significant amount of water. It could be a water-rich world with deep oceans, or even an ice-covered surface hiding an ocean beneath. Similarly, GJ-1214b, a sub-Neptune just 40 light-years from Earth, has been studied extensively for signs of water. While its atmosphere remains mysterious, scientists believe that its density suggests a water-rich interior, possibly with a thick atmosphere of steam. These super-Earths and sub-Neptunes represent some of the most promising candidates for finding water-rich worlds outside our solar system. As we continue to study their atmospheres and surfaces with new technology, we may soon discover signs of water, and possibly life, on these distant planets. The search for life on water-rich planets. Water is the key ingredient for life as we know it, and finding it on distant worlds is one of the most promising signs that these planets might harbor life. While Earth is the only known planet where life exists, the discovery of water-rich planets opens up the possibility that life could evolve in environments very different from our own. On water worlds, life might take on forms that we can scarcely imagine. Instead of land-based ecosystems, entire biospheres could exist in the oceans, from surface-dwelling microorganisms to deep-sea creatures that thrive near hydrothermal vents. These planets might lack the familiar structures of mountains and forests. Water-rich planets, oceans beyond Earth. Water, the foundation of life as we know it, is not unique to Earth. In the vastness of the cosmos, scientists believe there are entire planets where water is not just present, but abundant. These water-rich planets, sometimes referred to as ocean worlds, represent some of the most intriguing destinations in the search for life beyond our solar system. Imagine worlds where oceans stretch unbroken from horizon to horizon, where the land, if it exists at all, is submerged beneath kilometers of liquid water. These alien oceans, while familiar in substance, could hold secrets and surprises far beyond our understanding. The science of water worlds. Water-rich planets are believed to have formed in the colder, outer regions of their planetary systems, where water ice was plentiful during the formation of the planet. These worlds may have migrated closer to their stars over time, bringing their vast reservoirs of water with them. Unlike Earth, where water covers roughly 70% of the surface, but remains relatively shallow in comparison to the planet's overall size, water-rich planets may be dominated entirely by deep oceans. Oceans that could be hundreds, even thousands, of kilometers deep. In these worlds, water would likely be a fundamental part of the planet's structure, creating unique layers of ice and liquid depending on the temperature and pressure. Beneath the vast surface oceans, immense pressures at deeper levels would force water into different forms, such as high-pressure ice, which is not the frozen water we know but a denser, more solid form of ice that can exist even at high temperatures. This layering effect could create entirely alien ocean ecosystems, where life might thrive in environments more extreme than anything found on Earth. Some water-rich planets may even contain an ice mantle, a layer of ice beneath the liquid water, formed by the immense pressure of the overlying ocean. Such a planet could still have active geological processes below this ice mantle, similar to Earth's mantle and core. In these cases, hydrothermal activity could occur where the planet's internal heat causes cracks in the ice, releasing heat and chemicals into the deep oceans above. Such environments would be similar to Earth's deep-sea hydrothermal vents, where life thrives despite the absence of sunlight. Oceans that cover the world. Imagine standing on the surface of one of these planets, if you could. The view would be unlike anything you've ever seen. An endless expanse of water stretching out in every direction, with no land in sight. The atmosphere might be thick with moisture, constantly feeding the ocean below with rains or creating immense clouds that hover above, reflecting the light of a distant star. The color of the water could vary depending on the planet's chemistry and the light of its sun, from deep blues to greens or even darker hues, colored by unknown elements or biological life lurking beneath. These water worlds could have unique weather systems, driven by the interaction between the ocean and atmosphere. Without land to break up weather patterns, massive storms could form, with winds and waves far more intense than anything we've seen on Earth. On some water-rich planets, superstorms could last for centuries, driven by constant heat exchange between the ocean and atmosphere, creating monstrous waves and towering clouds that spiral across the surface. The deeper oceans would likely be completely alien environments. On Earth, our deepest oceanic trenches extend about 11 kilometers below the surface, but on water-rich planets, these depths could be multiplied many times over. At such depths, light from the surface would be entirely absent, creating a dark, pressurized world where exotic forms of life could evolve. Chemosynthesis, a process where life forms derive energy from chemicals rather than sunlight, could be widespread, just as it is at Earth's deep-sea vents. The creatures on these planets, if they exist, might be adapted to live in complete darkness and under incredible pressure. They could be unlike anything we've ever encountered. Large, slow-moving organisms that glide through the deep waters, or entire ecosystems based on floating mats of microbial life drifting just below the surface. The possibilities for life on such planets are vast and as yet unexplored. The atmospheres of water-rich planets. The atmosphere of a water-rich planet would be an essential factor in determining its habitability. In many cases, water worlds may have dense, thick atmospheres rich in water vapor, creating a greenhouse effect that keeps the surface warm and stable, even if the planet is far from its star. The James Webb Space Telescope and other future missions will allow us to study these atmospheres in detail, searching for signatures of water vapor, clouds, and other gases that could indicate the presence of oceans and potentially life. On some water-rich planets, the atmosphere could be in constant flux. The vast surface oceans could contribute to rapid evaporation, creating an atmosphere heavy with moisture. This moisture could condense into massive cloud systems that circle the planet, creating endless rainstorms and contributing to the planet's dynamic weather. In some cases, these atmospheres could be so thick with water vapor that they create a steam world, where the surface is a boiling ocean of water vapor and liquid, surrounded by towering clouds. In more temperate water-rich planets, the atmosphere might resemble Earth's, with a balance of nitrogen, oxygen, and water vapor, possibly giving rise to clouds, rain, and even snow. However, the lack of land to anchor weather systems could mean that the entire planet is subject to frequent and powerful storms, with winds and waves far stronger than anything seen on Earth. In terms of habitability, the presence of liquid water is a key factor. But the atmosphere also needs to protect the surface from harmful radiation and provide a stable environment for life to thrive. Water-rich planets orbiting M-dwarf stars, which are known for their intense flares and radiation, would need a thick, protective atmosphere to shield the oceans from these bursts of energy. In some cases, the thick atmosphere of a water world could help regulate temperatures and protect against such radiation, allowing life to evolve in the oceans below. Europa, Enceladus, and the ice moons, clues from our own solar system. While exoplanets with vast oceans are a tantalizing prospect, we don't have to look far from home to find examples of potential water-rich worlds. Some of the most intriguing candidates for oceans beyond Earth lie within our own solar system, on moons like Europa and Enceladus. Europa, one of Jupiter's largest moons, is covered in a thick shell of ice. Beneath that icy crust, scientists believe there is a global ocean of liquid water, kept warm by tidal forces from Jupiter's gravity. The Europa Clipper mission, set to launch later this decade, aims to investigate Europa's subsurface ocean, searching for clues about its composition and whether it might harbor life. If Europa's oceans contain hydrothermal vents or other sources of chemical energy, it could be a prime location for extraterrestrial life, living in the dark, cold waters beneath the ice. Similarly, Enceladus, a small moon of Saturn, has captivated scientists since the discovery of water ice plumes shooting from its south pole. These plumes, which contain organic compounds, are thought to originate from a subsurface ocean beneath the moon's icy crust. The heat required to keep this ocean from freezing likely comes from geological activity, similar to what we see in Earth's oceans near hydrothermal vents. These plumes have been sampled by the Cassini spacecraft, and the findings suggest that Enceladus could be another potential home for life. While these moons are much smaller than the exoplanets we imagine, they offer critical clues about how water-rich worlds might form and behave. Studying Europa, Enceladus, and other ocean moons gives us a blueprint for understanding how deep oceans can exist in environments far from the warmth of the sun and how life might thrive in such extreme conditions. Super-Earths and sub-Neptunes, likely water-rich planets. Many of the exoplanets discovered by the Kepler Space Telescope and other missions fall into a category known as super-Earths or sub-Neptunes, planets larger than Earth but smaller than Neptune. These planets are thought to be some of the most likely candidates for water-rich worlds. Their size and density suggest that they may have large amounts of water, potentially covering their surfaces or existing as thick layers beneath the atmosphere. For example, the exoplanet Kepler-22b, located in the habitable zone of its star, is believed to be a super-Earth with a significant amount of water. It could be a water-rich world with deep oceans, or even an ice-covered surface hiding an ocean beneath. Similarly, GJ-1214b, a sub-Neptune just 40 light-years from Earth, has been studied extensively for signs of water. While its atmosphere remains mysterious, scientists believe that its density suggests a water-rich interior, possibly with a thick atmosphere of steam. These super-Earths and sub-Neptunes represent some of the most promising candidates for finding water-rich worlds outside our solar system. As we continue to study their atmospheres and surfaces with new technology, we may soon discover signs of water, and possibly life, on these distant planets. The search for life on water-rich planets. Water is the key ingredient for life as we know it, and finding it on distant worlds is one of the most promising signs that these planets might harbor life. While Earth is the only known planet where life exists, the discovery of water-rich planets opens up the possibility that life could evolve in environments very different from our own. On water worlds, life might take on forms that we can scarcely imagine. Instead of land-based ecosystems, entire biospheres could exist in the oceans, from surface-dwelling microorganisms to deep-sea creatures that thrive near hydrothermal vents. These planets might lack the familiar structures of mountains and forests. Of water worlds, we stand on the edge of discovery, looking out into the cosmos and asking one of the most fundamental questions: where else might life exist? Water, the key ingredient for life as we know it, is not confined to Earth. It's out there, scattered across the universe, forming the oceans of distant alien worlds. These water-rich planets, also known as water worlds, invite us to imagine life far from the shores of Earth, in places where water doesn't just fill oceans and lakes, it dominates the entire planet. A water world is a place where liquid water covers nearly the entire surface, or perhaps lies just beneath a thick layer of ice. These planets form in regions of space rich in water ice, and over time, through planetary migration or gravitational interactions, they find themselves closer to their stars, where the ice melts into vast, deep oceans. It's a process that began in our own solar system, with the icy moons of Jupiter and Saturn, and extends to the exoplanets we are now just beginning to discover. Oceans deeper than imagination. On Earth, the ocean's deepest point, the Mariana Trench, plunges nearly 11 kilometers below the surface. Yet on a water world, oceans might extend hundreds, even thousands of kilometers deep. Imagine a planet where the water doesn't stop at shallow depths, but continues downwards through layers upon layers of liquid, until the pressure becomes so great that the water itself changes form. At these immense pressures, water enters what we call high-pressure ice phases. It sounds counterintuitive, ice forming in an environment of immense heat and pressure. But under these extreme conditions, water solidifies in forms that we don't see on Earth, creating new types of ice that are more dense than the liquid above. This layering, liquid water on top, high-pressure ice below, could shape the entire geology of a water world. On Earth, tectonic plates move over a molten mantle, creating the dynamic geology we are familiar with. But on a water world, these tectonic plates might instead glide over a layer of ice, with no land masses breaking through the surface to form continents or islands. Instead, an endless, world-spanning ocean would stretch out in all directions, the liquid surface forming the only landscape. Beneath the surface, deep in the abyss where no sunlight penetrates, life may exist in environments shaped by chemical reactions and internal heat rather than sunlight. Just as life thrives at Earth's deep-sea hydrothermal vents, where organisms draw energy from the Earth's internal heat rather than the sun, life on water worlds might exist in deep, hidden ecosystems. These could be entirely different from anything we've ever seen, yet bound by the same chemistry of life: carbon, water, and energy. Atmospheres and climate, a world of constant change. But these oceans don't exist in isolation. The atmospheres of water worlds play a crucial role in determining the planet's climate and the potential for habitability. A thick atmosphere, rich in water vapor, could envelop the planet, creating a runaway greenhouse effect that traps heat, warming the surface and potentially turning the entire planet into a steam world, a place where the surface is not liquid water but an ocean of vapor. These steam worlds may still have oceans beneath their dense atmospheres, but reaching them would require descending through thick clouds of steam, where temperatures and pressures soar. On a more temperate water world, the atmosphere might resemble Earth's, with balanced amounts of water vapor, nitrogen, and possibly oxygen. These planets could experience dynamic weather systems, constant rainstorms, powerful winds, and enormous cloud formations that swirl across the surface, fed by the endless supply of water. Without land to break up these patterns, storms might grow larger than any we've seen on Earth, with superstorms lasting for years, driven by the interactions between the atmosphere and the ocean below. The interaction between the atmosphere and ocean could also create deep circulation patterns, where warm water from the surface sinks into the depths, while cooler water rises in upwelling currents. These movements would influence not just the climate, but potentially the ecosystems within the oceans, providing nutrients and energy to sustain life throughout the water column. A silent, hidden world. The greatest mystery of water worlds lies beneath their waves. What kind of life could exist in a world without land? Could life on such planets evolve in the same way it did on Earth, where land-dwelling species diversified and adapted? Or would the ocean be the only environment these life forms ever know? In the deep, dark oceans of a water world, sunlight might be a distant memory. If the planet is far from its star, or if the atmosphere is too thick, no light would reach the depths. Life in these oceans would need to rely on chemosynthesis, a process where energy is derived from chemical reactions rather than sunlight. On Earth, chemosynthetic bacteria thrive near hydrothermal vents, drawing energy from the chemical compounds emitted by the planet's internal heat. On a water world, life might evolve to take advantage of similar processes, existing in isolated pockets near sources of geothermal activity. Heat and chemicals rising from the planet's core, warming the deep ocean and providing the raw materials for life. But these environments could also present their own challenges. The lack of sunlight means photosynthesis, one of the fundamental processes for life on Earth, would not be possible, and life might evolve in ways that we can't yet predict. Complex ecosystems could exist in these hidden depths, entirely separate from the surface world, where the interplay of heat, chemicals, and pressure creates unique conditions for survival. The search for water worlds. With missions like the James Webb Space Telescope, we are now closer than ever to finding these water worlds. Through careful observation of distant stars, we can detect planets that fall within the habitable zone, the region around a star where conditions are right for liquid water to exist. We can analyze the light from these planets as it passes through their atmospheres, searching for signs of water vapor, clouds, or other gases that might hint at the presence of oceans. In our own solar system, the icy moons of Europa and Enceladus, with their hidden oceans beneath thick layers of ice, offer tantalizing clues about what water worlds might look like. These moons may harbor liquid oceans, warmed by the internal heat of their parent planets, and scientists are eagerly awaiting the results of upcoming missions like Europa Clipper, which will explore these icy moons in detail. But the search for water-rich exoplanets takes us even farther from home. Planets like Kepler 22b or GJ 1214b are prime candidates for water worlds. Super-Earths or sub-Neptunes with thick atmospheres and lower densities, suggesting the presence of vast amounts of water. These planets are located in the habitable zones of their stars, meaning that liquid water could exist on their surfaces. If they are indeed water worlds, they may hold the key to understanding how common life is in the universe and what form that life might take. Life beneath the waves. As we continue our search for life beyond Earth, water worlds represent one of the most promising environments to explore. With vast oceans, complex climates, and unique geological processes, these planets could harbor life in forms that are completely alien to us. Life on a water world might never know land, but it could thrive in the darkness and pressure of deep oceans, in ways we can only begin to imagine. Through the study of water worlds, we are expanding our understanding of what life can be, how it might adapt, evolve, and survive in environments far different from our own. In the depths of these oceans, we may one day find the answers to one of humanity's greatest questions. Are we alone? Or is life thriving in the uncharted waters of distant worlds, waiting for us to discover it? Water worlds are not just a possibility. They are likely abundant in the universe. And as we gaze out at the stars, we are reminded that the cosmos holds more than we could ever dream. Somewhere out there, entire planets are covered in oceans, silently waiting for us to find them. Through this window, we've glimpsed the infinite possibilities of the universe, distant stars, mysterious exoplanets, and the enduring questions of whether life might exist somewhere out there. Each new discovery brings us closer to understanding our place in the cosmos, reminding us that space exploration is not just about the stars, but about unlocking the secrets of life, existence, and the future. As we continue to peer into the vast unknown, every mission, every telescope, and every new planet brings us closer to those answers. So, join us as we journey through the cosmos, uncovering the mysteries that lie beyond. If you enjoyed this journey through space and want to stay updated on the latest in space exploration, subscribe to our channel and hit the notification bell so you never miss a video. There's a whole universe out there waiting to be explored, and we want you to be part of it. Thanks for watching.